take a standard vacuum pump, which looks something like this, then we have the electrical motor on the back and the compressor on the front. On the top we have a handle, and on the bottom we have a support base. We then have an inlet which connects to the system to remove the air, and then above the compressor section we have the exhaust or the outlet. On the front of the compressor section we find an oil sight level glass so we can tell how much oil is in the chamber as well as its condition. As we take the unit apart, we can see that we have a fan and protective casing mounted at the back of the motor. Then inside the motor we have the stator which holds the copper coils, but we're going to look at this part in detail just shortly. Concentric to this we have the rotor and the shaft which drives the compressor. At the front we have the compression chamber. This is the two-stage compression version which allows us to pull a deeper vacuum, so we therefore have two compression chambers. Inside the chambers are the compressor rotors and the vanes which move the air out of the system. On top of the compression chamber is a reed valve which vents the exhaust. When we remove the fan's protective casing, we see that the fan is connected to the shaft which runs through the pump. The fan is used to cool down the electrical motor, and it will blow ambient air over the casing to dissipate this. The fins on the casing increase the surface area of the casing, which allows us to remove more unwanted heat. Inside the motor we have the stator, which is wound with copper coils. When an electrical current flows through the copper coils, it will generate a magnetic field. The rotor is affected by this magnetic field, and this forces it to rotate. The rotor is connected to the shaft, and the shaft runs along the length of the pump from the fan all the way up to the compressor. This way, when the rotor rotates, so will the compressor, and that's what we're going to use to create the vacuum effect and evacuate the air from the system. Just to note that when we think of a vacuum, we usually think of a sucking force, but that's not actually the case, and we're going to see why just shortly. If we look inside the compressor, we can see we have the inlet, which is connected to the system we're evacuating. Then we have the outlet and the reed valve, which vents the air and moisture which is being evacuated from the system. In the center, we have the compression rotor and the compression chamber. Notice the rotor is eccentrically mounted inside the chamber. This means it isn't perfectly central. That's a key feature which we'll see in detail just shortly. The shaft connects to the rotor and will cause it to rotate. Mounted inside the rotor are two spring-loaded vanes. The springs are always trying to push the vanes outwards, but they're held in place by the compressor chamber walls. Therefore, the tips of the vanes are always in contact with the wall, and there's a thin layer of oil which helps to form a seal between the two. When the rotor rotates, the springs continue to push the vanes outwards, so the vanes will follow the contour of the compression chamber. When the pump starts, the rotor is going to move across the inlet and expose an area inside the compression chamber. This area will be at a lower pressure compared to the pressure inside the system, so the air and moisture inside the refrigeration system is going to rush in to try and fill this empty region. So then why does it do this? Well, pressure always flows from high to low. So if we connected, for example, two balloons of different pressures, then the gases will move from the high pressure side into the low pressure side until both are of equal pressure. In this example, the low pressure side was a vacuum, but it didn't suck the gases in. The high pressure side pushed its way in. That's the vacuum effect. Gases want to equalize and will flow from a high pressure to a low pressure. Therefore, we use a vacuum pump to create a region of lower pressure so that the unwanted gases inside a refrigeration system will rush out of the system to try and fill this lower pressure region. So in our scenario, the connection hose and the new low pressure area within the compression chamber have become an extension to the refrigeration system. So the gases in the system are going to rush in to try and fill this and try and make that the same pressure between the two. But it's actually a trap, because as the rotor continues to rotate, the second vane sweeps in and traps that volume of gas in the chamber between the two vanes. The other vane then passes across the inlet and creates another low pressure region, so more gas rushes in from the system to try and fill this void. As the compressor rotates, the volume of the chamber is going to start to decrease. That's why the rotor isn't perfectly centered, so that we can vary the volume of the trapped gases. This decrease in volume is going to compress the gases into a tighter space. That will increase the pressure and the temperature. It continues to rotate into a smaller volume until the pressure becomes high enough that it forces the reed valve of the exhaust to open and the gases are then discharged. The compressor continues to rotate, and as it does so, the next batch of gases is pulled into the system and the cycle continues. Most vacuum pumps will be two-stage, which means there are two compression chambers linked in series. The exhaust from the first compressor links directly into the inlet of the second chamber. This design allows the pump to achieve a deeper vacuum. When we have a single compressor, the outlet is pushing against atmospheric pressure. But with the two-stage design, the outlet is pushing against a much lower pressure, because it's simply the inlet of the second rotating compressor, and the low pressure region is created during that rotation. As the vacuum pump continues to run, it will eventually pull the gases out of the closed system, which will reduce the pressure down below the pressure of the atmosphere, which is surrounding the outside of the system. As the pressure reduces, any moisture in the system will become easier to boil and evaporate. We can add a little heat with a heat lamp or a heat gun to help it vaporize, and that way we can extract it from the system. Okay, that's it for this video, but to continue your learning, then check out one of the videos on screen now, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, as well as theengineeringmindset.com.